Hello, everybody. Welcome to the session on what's your carbon debt. My name is Bronwyn Barry. I'm the board president of NAPHN and have been very pleased and honored to be able to assemble this very important panel. The collection of presenters that we're having present today is really focusing on some fantastic new tools available for our community to start to calculate not only the operational carbon footprint of buildings, but also the embodied carbon footprint. The International Energy Outlook published a graph in 2017 outlining the actual carbon footprint of buildings in the world, and operational energy, according to their pie chart, consumes 28% or emits 28% of carbon emissions, while building materials and construction, the embodied carbon material, apparently emits 11%. And putting these two together has become really critical as we move forward in our quest to help reduce the carbon footprint of our built environment. So we have three presenters today, starting off with Stacey Smedley. Stacey joins us from the Building Transparency Organization, which where she's the executive director. And the Building Transparency Organization is part of the Embodied Carbon Network, who is really spearheading a lot of the carbon footprint calculation work here in the US. So I'm really pleased to have Stacey come and present, and she'll be demonstrating the EC3 tool and sharing a bunch of other information that is really important for our community to access. Stacey's presentation will be followed by Jason Quinn. Jason is a former American, now happily living in New Zealand. So he joins us from our global Passive House community. He was an engineer at NASA prior to emigrating to New Zealand, where his company, Sustainable Engineering, is one of the Passive House certifiers operation working in New Zealand. And he will be presenting a tool called LCA Quick that has been developed in collaboration with Brands, the Building Efficiency Organization of New Zealand. And finally, we'll close with a presentation by Tim Martel. Tim comes to us from the UK Passive House community and has been working on a really fascinating tool called PHPP. Tim is a freelance chartered architectural technologist, and his work has been, his tool he's been developing in collaboration with the British organization known as AECB. So I'm looking forward to hearing all of your presentations, and thank you so much for joining us.
Right, thanks Bronwyn for that introduction, and I'm excited to start off this presentation today. Again, I'm Stacey Smedley, and I'm going to talk to you about work that we're doing here in the States around reducing the carbon footprint of every building. I always like to start with just grounding us in our impact. So, the building industry is a global industry, and we know over the next 35 years that over 2 trillion square feet of construction is happening worldwide. And just to kind of put that into perspective and really get a kind of picture in your mind, that's the equivalent of an entire New York City every 35 days for the next 35 years. So if we are imagining all of the materials that we are manufacturing and transporting and installing to create that amount of buildings every 35 days, every month basically, if we aren't thinking about the impacts of those material choices alongside the energy consumption of those buildings, we aren't truly being responsible. And as Bronwyn mentioned, we now know, based on these kinds of pies, that when you look at building operations plus building materials and construction, what pie charts are telling us is that that really is equivalent to about 40% of global CO2 emissions. But what we are also finding as we dig into this is that actually that building materials and construction portion actually spills over into transportation and industry. So it's actually a larger chunk than we might think it is when you're looking at it at face value. So it's just thinking about the transportation of materials from one plant to another plant, or from the plant to the construction site, and also some of those industry emissions associated with manufacturing of parts of a product that wouldn't be captured in that 11%. And just to kind of, I always use this cartoon graphic to really ground us in what we're talking about. I think for 30 plus years now, we've been looking at operational carbon, which is the carbon associated with the buildings once they're constructed. So their energy consumption, mechanical, electrical, plumbing systems, lighting, all those things that are consuming energy are really in this operational carbon bucket. And when we're thinking about embodied carbon, it's really everything up to that point. So it's the extraction of the materials, the transportation to manufacturing facilities, transportation to job sites, the installation of materials on a construction site, and then the emissions associated with the end of life of those materials. And then any use phase stuff that we're talking about too. So really, if we look at these pictures, it's everything except for this operational energy consumption that we're looking at when it comes to embodied carbon. And what we now know when we're starting to actually look at operational versus embodied carbon next to each other for buildings, that on average, if we just take an average snapshot of a kind of a single building globally, and average all the data around energy consumption and material emissions, if we're taking 2050 as our line in the sand where we have to get to zero, the embodied carbon bucket is 50-50 with the operational carbon bucket. So it's just as important, it's just as impactful. And once we emit those emissions during manufacturing and construction, there's really no taking them back. Unlike operational carbon, where we can start getting more efficiencies over time of the building's use, we really need to figure all this out at the time of design and construction. And we haven't been looking at it for as long or as deeply as operational carbon. So we have to catch up, and we have to make tools and inroads on embodied carbon as fast as we can if we're going to meet the 2050 deadline to get to zero. Just to ground everyone a little bit in terms of what embodied carbon looks like, there's all sorts of stages. People use terms kind of interchangeably, but there really are these different stages of this that we can think about. There's the upfront carbon, which is the A stage. That's really the cradle to gate emissions and the construction process emissions. There's then stage B, which is the use stage. So this is looking at materials replacement. How many times are you replacing that carpet tile or that roofing membrane, and are you adding that into your overall emissions calculations? And then end of life, which is really looking at when you tear a building down, what are you doing with those materials? Are you deconstructing so that you can reuse them? Are they being taken to a landfill, etc.? So all of that is embodied carbon. And again, we know that a lot of the emissions that we can impact right now, and actually the largest source of embodied carbon emissions, are really in this kind of A stage, this product stage. The tool that I'm going to show you, EC3, is really explicitly focused on this product stage where 80% plus of the emissions are likely to be. We want to reduce that product stage through specifications and procurement of low carbon materials. And then looking at the ecosystem of tools, there are a lot of tools when it comes to how to look at this. There are really good life cycle assessment tools out there right now in the world, including Tally, OneClick, and Athena. These life cycle assessment tools have average emissions data for materials, and then they're looking at all sorts of greenhouse gases, not just carbon. So they're really good if you're trying to make directional choices or systems choices early in design, like timber versus steel, or envelope system A versus B from an operational and embodied perspective, where you can get average and directional information and make good choices. What we couldn't find when I was at Skanska looking at this 2 years ago, Skanska is a global construction company, we were trying to figure out, once all those good early design decisions had been made, how do we actually take that? And if we know we're building a building out of concrete and steel with carpet tile and ceiling tiles, and things like that, how can we actually look at each of those materials and specify and procure the lowest carbon options? There wasn't really a tool that was doing that that we could find, and that's really where we see EC3 filling a gap. And really, you need to do both of these things, this early life cycle assessment to make really good system choices, and then this really good deep procurement plan to look at low carbon materials to really achieve embodied carbon reductions. By creating EC3, it started with seed funding from Skanska and Microsoft to create a tool that would be available to everyone, not just to these companies, a tool that would be easy to use and free to use, and really try to make it something that with a few clicks, people could actually make carbon reductions actionable. It's also open and transparent from the data side of things, and it has an API. So our tool and our database of emissions for materials can also be translated to other tools that might want to use it. And it's, again, focused on the supply chain portion, this A1 to A3 product stage. The tool was then turned over to the Carbon Leadership Forum, where the Embodied Carbon Network lives, and was managed there as a grant to get to public release with all these partners funding and piloting its development. So it was industry informed. We have all of the major kind of industry organizations and manufacturing companies supporting the tool and helping us make sure it works, both from a user side in the AEC community, but also from a materials side when it comes to how we're displaying their data. The tool was launched publicly in November of 2019 at the Greenbuild conference here in the States. We had some pilot users that we had helping us up to that point, and then you can see a waitlist developed, and currently as of this month we're at about 6,500 users. And you can see what's nice is that we are achieving our goal of it not being for just architects or engineers, but really something that folks across the AEC industry can start to use for their own purposes. What the tool is doing is really not complicated. It just wasn't available in a tool that we could find. So it's taking material quantities from estimates or BIM models and multiplying those material quantities by kilograms of CO2 per unit out of third-party verified environmental product declarations, or EPDs. So you can see here, if you have an EPD, you can find this 445 kilograms per cubic meter of concrete, do the math against your cubic meters of concrete for your project, and end up with an embodied carbon estimate. And this is really valuable during pre-construction on a project where you're doing cost estimating to all of a sudden also be able to do carbon estimating. Just to make sure everyone understands EPDs, they are like nutrition labels for materials, building materials, where they've got, again, a declared unit, which is kind of like a serving size, and a carbohydrate or a kilogram of CO2. And this is what EC3 bases all of its material emissions calculations on, our third-party verified EPDs. And the database currently holds, actually, it's over 23,000 EPDs now, because it's constantly growing as we get more EPDs digitally transferred into our tool. To sign into the tool and to register for free yourself, you can go to buildingtransparency.org. That's where the tool now lives. And again, just sign in and registration will become active almost immediately. And with that, I'm just going to go briefly into the tool to show you a little bit about how it works. So once you've logged into the tool, this is the current landing page. You're going to see that it gives you your name and your user type, and then also gives you that look at the publicly available EPDs in the database. We are currently building out more material categories, things like resilient flooring, masonry, etc. But these are the ones that we published first in the first public release. What you're going to see over on the side here are really two options that are important. One is find and compare materials, the other is plan and compare buildings. On find and compare materials, what you're able to do is actually query that EPD database. So if I go to concrete, I know I have ready mixed concrete. I know that it's the strength of exactly 5,000 PSI. And I know my project is in Washington State, for instance. I can click search. What it's going to return to me is basically a database query with those filters and showing me how many EPDs I have that meet that criteria, and then give me some information on the metrics around the kilograms of CO2 for that search. It's also going to let me go down here and actually look at each one of these specifically. If I wanted to open one up and say, okay, here's this EPD's number compared to the whole range of my search, so this is a pretty good product, I can do that. I can actually go view the digital version of the EPD if I like, or download the PDF. And you can also start to look at comparisons. So if you click on compare manufacturers, you're going to see that you can actually understand what manufacturers in a specific place have EPDs, look at their ranges of carbon for all of the EPDs in the database, and directionally look at Stoneway as maybe they're just a better lower emitting concrete supplier. So could we procure from them? Can we start to set bidding requirements that incentivize lower emission concrete mixes because we have data from suppliers? This is something you can do for all these material categories. If I do the same thing for carpet tile, you're going to see a similar process, just a few clicks. I'm going to say not Washington, but USA, and I click a button. And again, it's going to give me the range for that whole search. And it's also going to give me every single EPD that you can filter by product or manufacturer. And again, do that compare manufacturer, where you can start to look at manufacturers next to each other and understand who's really leading the way when it comes to emissions. We use this a lot to set limits, where you can say you must be under a certain kilogram per unit in a spec, or even just to require EPDs to know that there are enough manufacturers that meet requirements. The second feature is plan and compare buildings, where you can actually go in and create buildings like I showed. I'm going to open up my 9-year-old son Jackson's homework assignment that I made him do, where he created a lair for our dog Chuck. underground layer. And you can see here what this does is start to set up a project where you can put in an address. You can put in square footages to start to get to metrics like embodied carbon intensity, kilograms of CO2 per square foot. You input your particular material quantities and descriptions, do the searches for those materials to get to collections in your selected material directly from the building planner. And once you've done all of that, there's a few things you can do. You can visualize your project by impact. So this is a Sankey diagram where you've got the relative impacts of ready-mix concrete versus rebar versus your aluminum framing, etc. The white area is the potential reduction based on the supply chain, and that S is your selected product. So this is one way to look at your building and figure out where you should focus your attention on emissions, but also roll up to an actual reduction target that you could set based on available supply chain products today. And the last thing is the selected versus baseline, where you can open this and actually, once you've made choices, see a baseline that's been set by the Carbon Leadership Forum per material category that rolls up to a building baseline against that achievable number. That's the 20th% of the data, and then your actual realized savings based on the EPDs and products that you selected. So again, I know I only had 15 minutes, but I wanted to give just a brief overview of how the tool works and what it's doing. The last thing is just on the building transparency page under resources. If you click on downloads, you can actually go in, learn more about the tool through these primers, but also look at some template language you developed for EPD requests to manufacturers that don't have them yet, where we want to incentivize EPD production, as well as example language for bid documents and specifications, where you can start to add in language around EPDs and this kilograms of CO2. We're seeing on projects now that by using this, they're achieving about a 30% savings without a cost increase, just because they have the data and can start to build it into their process. And with that, I think I'll turn it over to Jason to continue the presentation.
Well, thank you, Stacy. That was a really good introduction. And I'm going to have to see if I can talk to some folks about using that tool here. We obviously don't have anything like that here in New Zealand. So in working through what I wanted to talk about today and how I want to do it, I thought first I'd start with a little bit of a story where I'm at. So I'm in this little country in the bottom right called New Zealand, although as you can tell from the accent, I'm originally from the United States. I grew up in Massachusetts. And it's interesting that New Zealand has a very similar climate zone system to Northeast America, as we call it, or Eastern United States. And so we range from a warm climate, like you have in, let's say, North Carolina, all the way up to the cool temperate climates up in Massachusetts, where I grew up. So we've got a couple interesting questions I wanted to address with these tools. Stacy showed us and Bronwyn talked earlier about how you've got 40% maybe of carbon total in buildings now, if you count also not only operational carbon and the embodied carbon that we calculate materials, but also the transport parts that are kind of added to that embodied carbon calculation. So we have those same kind of questions here in New Zealand. We have a relatively small country. We're talking like Eastern Massachusetts kind of size in terms of population, so relatively small. And we import a lot of materials. We import most everything we do. And the materials we do make here have very high embodied carbon. So our concrete has roughly twice as much embodied carbon as concrete would source in Europe, for example. And steel is also similar that way. The steel we produce here locally has a higher embodied carbon than steel in Europe. So when you look at that and you look at the world as a whole, you wonder, well, if the answer is one answer in Europe, is it a different answer in New Zealand? Is it a different answer in the United States? And of course, when you look at, Stacy just showed us that you can perhaps make different material choices in a building and achieve 30% reduction. That becomes a pretty interesting question. So we look at, if you want to answer a question like that, where you're not looking at just how the building operates on its own, but you want to look at how the building fits into the whole of its production life cycle, from where you get your stuff to where it goes when you're done with the building and its life cycle, then you need to do a life cycle analysis. So what it comes down to, right? You can't do just a nice PHPP tool model anymore, unfortunately. Tim's going to hopefully show us something that'll let us stick in that world a little bit longer. But I had this interesting question from that came up quite a few in seminars, which is, well, in New Zealand with our high embodied carbon for our materials, and we have a really clean grid, we have quite a bit of hydroelectric power in New Zealand, we get heaps of rain. So if we've got this really clean grid and we've got these really crappy embodied carbon materials, then is passive house still the right choice? So in order to do that, I had to learn how to use life cycle analysis tools. I'm not a life cycle analysis expert. I mean, Stacy is, and Tim, I think he's probably a cross between a life cycle guy and a computer programmer. We'll find out in a few minutes. But I'm a hacker. I pull together tools and I use them to solve engineering problems. That's what I do for my living. So when I had this problem to address, I was like, well, I need to do an LC analysis. So I need to find a tool to use. Well, luckily in New Zealand, at least, we have a tool that's been developed by our local brand, which is our Building Research Association of New Zealand. And they developed an Excel tool called LCA Quick. And as Stacy just showed us, an LCA tool to some extent is really just a giant sum if statement in Excel. So how much of this do you have? How bad is it per kilogram or per square meter of area? And then it gives you a result in terms of embodied carbon or waterway pollution or other damages that an LCA analysis can be used. We're going to talk just about CO2 here, and I know Stacy talked about embodied carbon as well, but LCA analysis can also be used to look at a lot of other kinds of impacts in the world. Now, when we're doing LCA analysis, the LCA analysis I'm going to talk about here runs from the forest, where you harvest the trees, or you dig get your limestone to make your cement clinker, all the way through the end where we're talking about recycling credit back to where we recycle parts of the materials and they go back into the system, or they go to landfill and finally get wasted as methane, right? As things rot down in a landfill. So we're taking that whole big picture. When we do PHPP, we only look at the use stage, the operational use stage. So by having an LCA tool, we can look at the whole big picture. So again, it's relatively simple. What I did is I took a PHPP file with variants, and already in PHPP, we already have the ability to calculate the operational energy of the building to some level, right? We have assumptions about occupants and how they use the building. We know that the heating and cooling energy is accurately predicted. And then we can easily calculate, well, we have this much energy used of this type, so it has this carbon emissions based upon the grid carbon intensity. Now we just have to get materials out. Well, luckily in PHPP, if you're looking comparing building to building, you already have the ability in the variance package to look at material thickness changes. Like the insulation gets thicker, the timber gets thicker. That's already built into PHPP. So all you have to do is to take that and calculate material quantities and link that to another tool. In this case, LCA Quick, because it is a Excel tool as well, I could just link to have the energy consumption from PHPP go into LCA Quick as an Excel tool, and the same thing for the materials I was changing as I went along. And then from the LCA tool, I could look over the building's 60-year lifespan that's used in the LCA Quick, what the impact was for each phase of that building. So this graph across the bottom of the page has, the A phases, which is the production, the material phases, and the B phases is the use of the building itself, whether it's the base building or the tenant's energy use. They've broken out separately here. And then finally, the energy being in deconstruction and reuse of the energy. So D is reuse of the energy, as it were. And if you look at this particular building here, is a building in New Zealand where it has really high operational energy use. Our building code's not terribly great. So buildings tend to have fairly large operational energy use, especially if you assume that you're going to heat them all the time, which is not common. All right, so in setting up my LCA problem that I wanted to look at, I needed to go ahead and decide what I was going to do in this space. So I decided I would do six cases, 6 variants, just like we do in a PHP tool. Right? It's not a big deal. And I'd look in that. I just wanted to see, well, is passive house really the right choice? So I ran a New Zealand code building, one that's slightly above code, like you would typically see in being sold on TV. Our building's better than the guys next door, but only a little bit. And then one that uses twice as much energy as a passive house. And then finally, the certified passive house energy level. And then half of that. So if I did twice as, I had half the energy of a passive house, heating energy. And I should say I did this with certified passive house buildings. I had access to the PHP files and I got permission to do that. So when I ran those 6 cases, I was just changing the things that change between buildings. So unfortunately, that means that if I had a concrete slab, it was the same slab in every building. So the concrete slab wouldn't change between buildings because we're talking just about we're talking about putting more materials into the building to reduce its energy use. So this is a building in a cool temperate climate in New Zealand. It's a timber frame building with a brick veneer. It's a relatively common construction in New Zealand. It has an XPS insulation on the floor and fiberglass and timber for the rest of the building's insulation because it's reasonable size, it's reasonable form factor. So then with the LCA tool, you can plot both the carbon in it as well as the power energy. So if we look at here, the red dotted line is the operational kilowatt hours per square meter per annum that PHPP puts out, right? So it's just dropping down from, well, actually you can see the New Zealand code version would be completely off the top of the chart. So it's just crazy. So when you get down to passive house, which is at 5, and then you get case 5 is the passive house level, and case 6 is half of that. And then you can cross plot easily looking at the total carbon emissions. And as you'd expect the carbon emissions to go down, especially when energy use for operational use is off the top of the charts. But what happened is it went down as you added more insulation and the operational carbon decreased over its 60-year span. But it doesn't actually flatline out. So in this case, even cutting the energy use to half of the operational use, it still made sense to add more insulation, to add more, tiny bit more of XPS foam, tiny bit more fiberglass and timber on the walls. It kept going down, which wasn't the case I expected. And there's just some other ways to plot that. So if we look at another building, this is a building in a warm temperate climate in New Zealand, and this is a structurally insulated panel building. So this has EPS foam insulation on the walls between some oriented strand board. Everybody knows what SIP construction is, I'm assuming. And then it's got a concrete slab over an EPS foam insulation system below the slab. And then finally, it's got a truss roof with fiberglass insulation. So it's got similar form factor and size as the previous building. With different constructions, you wonder if you get a different solution. In this case, again, because you have PHPP running, you can easily calculate the operational carbon in PHPP, and it goes down all the way down to the case. In this case, because the building is in a warm temperate climate, the starting case in New Zealand code is actually on the chart, which is nice. And then if you look at the overall carbon emissions, including both operational and embodied, the line does more what you'd expect, which is it comes down to a minimum and goes back up again. So this says that between case 4 and case 6, which is the case that uses twice as much energy as a passive house, and the case that uses half as much energy as a passive house, somewhere in that area is the low point for this particular building. And you can see the dashed line is the embodied carbon. I mean, the dotted line, I'm sorry, with the dotted black line at the bottom is the embodied carbon. So that is showing that basically what happens is as you want to get to half of passive house, that cranks up significantly, the slope changes. And that's because you're adding quite a bit of EPS insulation into the walls and floor of the building. All right. I wanted to stop now and talk about some of the things in this study that sucked, because like all studies, when we do engineering studies, we can only answer the questions we design the study to answer. So when I did this study, I was specifically looking to address the question about where's the right point for insulation levels. So if I take a building I'm already going to build, and I'm already going to use those materials, I'm already going to use New Zealand concrete and New Zealand steel, which is really high embodied carbon. I'm already going to use the New Zealand grid, which is fairly green. Where should I stop? Is passive house actually the right point? Or I actually figured that low energy building would be a better point for New Zealand because of our clean grid. And I was surprised that the answer is actually probably below passive house in most homes for the lowest the lowest overall carbon emissions. So where that optimum is. But what I didn't do is I didn't look at, and it's excluded from LCA, is a lot of garbage in, garbage out. So LCA calculations can only represent what you put in. So if the EPD is wrong, or if you use the wrong EPD, you can't get the right result. In this case, the LCA calculation, I didn't look at changing the XPS in the floor system for that timber frame building, which had XPS above the concrete slab, to EPS, for example, which is a very simple choice, right? Or I didn't look at the fact that some XPSs, actually most XPSs we use, insulation we use in New Zealand is imported from the United States or China and uses HFC blown. And you'll be able to see that in the EC3 database, that has much higher embodied carbon impacts because of the global warming potential of the blowing agent versus a CO2 blown XPS, which we import from the United Kingdom, from where Tim is actually. And so if you look at that, that can be a huge impact, but I didn't look at that. I just looked at changing the thickness. The same thing, I didn't look at changing the XPS out for EPS. I just looked at changing the thickness again. And the things that had the biggest embodied carbon impact on this building you would expect weren't included, right? So I neglected steel and the concrete because it was the same for every building. I only varied the things that varied. So be really careful when you're looking at a life cycle analysis result that you understand what the person actually varied in that calculation, because it's always garbage in, garbage out. One thing I've noticed for a few LCAs I've looked at here in New Zealand is that actually, to my knowledge, all of this is refrigerants almost always excluded. So if you've got a cooling system that's using a high global warming potential refrigerant in it, that's excluded from the LCA analysis. They don't count the fact that the mechanical system's leaking a lot of HCF, I'm sorry, and that's causing a high global warming potential, and they've got to replace that because it's a supermarket, let's say, or something, right? Where they use a lot of refrigerant, and that can have a huge impact. Mechanical systems are excluded. I've got good and bad. I want to point out a couple of good and bad news about that. The good news is usually it doesn't have a huge impact. There's been a study done, at least the only one I'm aware of is one from the UK, where they looked at mechanical systems and the impact was fairly small in the overall building embodied carbon. But it is excluded. So if I compared a building with and without an MVHR system, well, the LCA would say they're exactly the same, because except for the operational energy impacts. because they're not in the LCA analysis. And finally, the EPDs don't always include everything. So if you look at an EPD for timber, for example, it doesn't, and Stacy, we can talk about this in the end, I hope, it doesn't include the forestry impacts. So an EPD that says you've got so much carbon in the timber that's being stored, and then you've got this biogenic storage that's going on. You also have the problem that if your forestry practice was bad practice and you actually caused that forest to emit quite a bit of carbon out of the soil, that's not captured by the LCA. It's only capturing the harvested timber as well. So a lot of things, even though LCA is supposed to cover everything, and it can, we still have boundaries on the system. We're excluding those effects. So it's really important that we take that into account. Well, that's what I wanted to say. Thank you very much. I'm looking forward to see what Tim has to say next.
Thanks very much, Jason. So I'm Tim Martel. I'm a passive house designer. I'm also a chartered architectural technologist. I spent a little bit of my earlier career as a programmer in Visual Basic, and that is what I've been basing on some of this on. Turns out it's the language that's native to Excel, so Excel comes with it whether you want it or not. And I'm going to be talking about this AECB product, PHRibbon. PHRibbon does quite a lot else apart from embodied CO2, but there is one part of it. There's one button here. Here's the ribbon itself. It's a toolbar essentially that gets installed into Excel and does lots of things. The embodied CO2 part then produces these graphs, and it's part of this larger tool. It's also been modified so that it works in US imperial units. It's got the optional module for embodied CO2 in it. So I'm going to look at just the whole life assessment, just to remind you, just as we had in other presentations, what it covers. So we've got the product stage, construction stage, use, end of life, and system benefits beyond the boundary. If you were to graph that, A to 3 might look like this. This is the orange segment here is also shown on the graph. For 3 different types of building: a masonry building, a SIPS-based building, and timber and cellulose building. And if you were to add in the transport to site, it would look like that. That's the A4 to A5. And then if you were to add on the use of the building and end of life, you'd get that. And what's interesting is for passive house, there is a construction method which is quite common here in the UK. Don't know how common it is in the US. But timber and cellulose has quite a large end of life stage C there, and it's very important. And that's also got quite a large carbon storage, A1 to A3, which is the timber being stored, and this is the timber being incinerated at the end of its life, assuming that that's what happens. The standard assumption at the moment, using our national standards, there's an organisation called RICS, Royal Institute of Chartered Surveyors. They've set, in their standards, they set out that timber would get incinerated, 75% of it would get incinerated. But of course, that could be changed for different regions, and so that could be customized for every state in America. And there's customization is part of the tool. So PHRibbon deals with this whole A1 to C4. It can also include stage D if the information is available. It's not often available, at least in this country. I'm now going to go through just a little bit about a little demo of what it's like to use, because often that's quite an important thing. How easy is it to actually get results out of? This is the US Imperial Units version. And you can see when we look at the R values tab, we've got materials entered in here. And this is just the standard way it's done in PHPP. And if we start the tool, which is just up here, got all the other things, embodied CO2 here, we can start a new calculation. It gives us the chance to start a new calculation there. We add a new materials here, and it's created another tab. It's created an embod tab. All these tools in PHRibbon work directly on your PHP. They don't need a special PHP. They just work wherever you are in whatever you've got. So this one, it's starting to take the first construction from the first R value that we had in there, and it will try to match up these materials automatically. So if we go to gypsum, it'll look for gypsum in there, and it's found it and it's matched it up. That'll be fine, that one. So we write that selection, it'll write that line, and it's taking the quantities. So if you look at this quantity here, it's added that in, and it's taken that information from the PHP. It's also taken the thickness of the material from the PHP. Cellulose is the next one. You've got several choices here when it comes to cellulose. The one we want is volume filling in walls. The PHRibbon remembers associations you make. So if you choose this one and write the selection, next time you choose cellulose, it'll guess that you want to use that association again. So that can help speed up a few things. Also, when you want to add layers together, so this cellulose is the same as this one, is the same as this one in this section. So we've got 3 sections like you usually have in PHP. You could just add them together by just clicking that there. So write that selection, and then when you look at the thickness there, it's added them together. You can add in, we've got battens here. If we put in battens, it doesn't recognize 2x4, unfortunately, but if we put in a batten, then it does recognize that, and we can enter the spacing for that. So 24 inches, and the width, let's say it's 1.5 inches. And we can add that to this one here, write that selection. And then we could also add the sheathing there, and we could add in whatever sheathing material that is. So then within the software, you then, after you've added that, and there's going to be next, there's going to be other R values that are in there to be put in. So you can go through those until you finish that. When you finish that, you'd go back to the main menu, add your windows. There'll be a selection of windows that could be put in. You could add in PV as well. And it'll assume for the moment that all your windows are going to be that, but you can choose a part of it and then change the quantity later if you want. There's also a few things which aren't in PHPP. So although we're using PHPP for the quantities of these materials, as it's quite a good approximation for that, although it does use external areas. Of course, PHP, everything's measured externally. So some of them are a little bit overestimated, but then you've also got wastage on site. So it's probably reasonable to do that. When you get to intermediate floors and roofs and internal walls, those aren't actually included in the PHP as such because they're not thermal elements. So this section allows you to add those in, and so if you had your overall roof covering might not even be mentioned in the PHP. You might stop at the ventilated layer. So you've got another set of materials here which allow you to enter that, and then you'd enter the area of that later. So you'd say write that selection there, and it'll add that in, and that yellow cell is a reminder. It's that you've got to enter something in there a bit later. So what I'm going to do now is just go back to the main menu and summarize. After you've finished all that, you would go to the summarize button, and it would write all these sections, write the graph, and actually at the moment we haven't got very much data in there, so it's hardly anything. What it will do is write stages A1 to A3 up the top here, and then the transport to site there, stages B1 to B4, and stage C, which is the quite important one for end of life, particularly in timber, that's down there, and it will create this graph here. So let's have a look at some of those results. What we have is the orange ones are the A1 to A3, and in this particular one over here, we've compared timber and PIR construction with a cavity wall. And it may not be immediately obvious, but actually this one is a better result than this one, because using the REBA standard in the UK, REBA 2030 uses this RICS calculation method. It's permissible to take off the timber, because that timber storage counts against this C, this end of life stage here. So it's stored here and then released here. So that's fair enough, but you can only do that with a full life calculation. You can't take off timber if you're not actually dealing with the end of life. It's not really fair. So when you add all those up, you get 281, and when you add all these up, you get 358. So this is actually a better result. Similarly, with this one, this timber, in this one, we've got a breakdown of the materials over on this side, and that's just showing you that quite a lot is going on with the timber down there, and that's contributing to this stage C here. And again, in this one, with a timber frame with brick cladding, the brick is contributing a little bit, but it's mostly the concrete that's doing it there. So it's not the height of the bar that's important. It's the actual overall result, which is also calculated in the software. You can do the same with, you can combine this with the operational energy of the building, because of course PHPP calculates that already. And this isn't actually part of PHRibbon, but you can use the data to combine the two. So the embodied CO2, well, the embodied CO2 of the construction materials would be this part here, and then the embodied CO2 would actually be all the way through the life there, and then also at the end of life here. But in this one, what we're doing is we're rather simplistically comparing a passive house development here with a normal building code example here, and you can see that the rate of because it's a passive house, it's actually contributing to CO2 emissions much slower during its operational life. Actually, interestingly enough, because of the choice of construction method, the passive house one didn't actually cause any more CO2 emissions for its embodied CO2 at the start. It was about the same, and that was just because we used a timber construction method, whereas the normal construction method wouldn't have been timber, it would have been more concrete block, which would have been more intensive anyway. So it worked out the same, you know. And the overall contribution of embodied CO2, it depends on what the life of the building is, how long you say the life of the building is, if it's a standard life or 120 year life, and obviously more to do with the materials. So if you like more information on that, there is a website for it, and the website here is will have some videos and some more details about all of that and all the features in there, including quite a lot about embodied CO2 as well. So thank you very much.
Thank you, everybody. That was just fantastic and exactly what I was looking for to bring together in this panel. So we have some time left, and I'd like to follow up with some questions to our presenters based on the just wealth of information they've shared here. So starting with Stacey. Stacey, what was really apparent in your presentation was the real benefit of the data transparency. And this, it's really clear that once people have that information, they can make much better choices. And the 30% reduction that you quoted for actually no extra cost. Have you got any other stories about how this is really transforming the choices people are making about their building materials?
Yeah, I mean, we're seeing all sorts of case studies now of positive impact. So the first is just the ability during pre-construction where you're looking at cost and product choices to also have the carbon emissions associated with those products in that same comparison chart, right? So an owner might have 3 products they're looking at for something, and they might have goals of, low cost, low carbon, and low toxicity. And, one product might not be all 3 of those things, but they can make an informed choice and say, okay, for this, we're going to really focus on that low carbon one, or for the next one, it's going to be the second highest cost, and that's okay. So it's just giving them a fuller kind of suite of data to make those choices. That's really what's leading to things being spec'd that allow the savings to happen. It's because they have assurance of this fact that they now have emissions numbers. Other ways it's helping with the transparency side is, we need more manufacturers and more products to be transparent about their emissions and get environmental product declarations. So the second part where we've seen success is for an owner or a design team that says, hey, we're using precast concrete, but we don't have any precast concrete EPDs. We want to be able to understand this for more than just an average. And we've had stories now where our precast concrete suppliers getting their EPDs just because the team asked for it, and now they know they're going to be the first supplier in the tool. So it's forcing this market transformation to incentivize the business case for this transparency, and then also incentivizing the reduction of emissions and materials. So it's competitive all of a sudden if everyone's being seen next to each other. So they're investing in these innovations that then doesn't drive the cost up for these choices. It just drives the emissions down.
Absolutely. Thanks, Stacey. And Jason, one of the things that was really apparent out of your presentation was the locally specific impact of product choices. It was fascinating to see how, because so much is imported in New Zealand, it completely changes the carbon footprint of materials. Can you speak more to if your assessment was run elsewhere, what would the relative difference be? And, how can we, Stacey's tool, I've also noticed you have Canada and the US, and maybe I'll come back to it's the second part, but Jason, maybe you can start with the local versus global impact and how this assessment really has to happen at such a locally specific level.
Yeah, I think probably that Stacey made that point more clearly than I did, that it's not only local, but it's also which manufacturer you buy from. So you can go for concrete manufacturer A might have half the embodied carbon of concrete manufacturer B for the same spec concrete and for not necessarily the same cost, which is pretty incredible. So for New Zealand, we have high embodied carbon, and I think when I include the whole building, it'll be different. I mean, in other words, it would change if I looked at the whole building from New Zealand to the United States. Because my study only looked at the differences from one energy consumption level to another, like taking a standard house and making it passive house, or actually taking passive house and making it standard, it has the same amount of concrete in it, it has the same embodied steel in it, it has the same carpet tiles. So I only looked at the things that change from making a passive house to a standard house, excluding the ventilation system. So that means the results should be the same in the United States, except for the operational carbon emissions for the energy use. So because our grid is fairly clean, because of our large hydroelectric power and more winds coming online, I expect that you'd want to actually go significantly past passive house in terms of energy consumption. So you'd want to actually drive the insulation well past passive house levels, not stop at passive house, not stop at 15. Maybe you should go to 8, which is an interesting
I think that's
solution.
A whole other discussion.
Passive house is just way too easy. You should do something more difficult, is basically the result. Yeah, it wasn't what I expected.
Great. And Stacey, just the quick question, and then I want to bounce it over to Tim as well, because the where you're assessing them, I wanted to ask, you've got the US and you've got Canada. Are there plans to add other parts of the globe into the calculator?
Yeah, we already are. So we wanted the public launch to be very specific and very complete when it came to the US Canadian market, just so that we weren't biting off more than we could chew all at once. But since then, we have started importing EPDs from everywhere. And there's actually an import EPD button once you log in, where anyone can upload up to 25 EPDs at a time. And they go right into our digital queue, and you can see how they're being translated into that digital format. And we want folks to start to do that from different places, so we can see where those hotspots are, where there's interest, and where people are starting to want that and demand the tool. So please go import your EPDs. We've got Europe, we've got some from Asia. I don't know if New Zealand's in there. If there's any concrete EPDs down there, that would be amazing. But we are open to that now, and it's really what the next stage is to scale.
Fantastic. And maybe Tim, you can tell us where you're sourcing your EPDs, and if you're connecting through the API with the Embodied Carbon Network, the building transparency tool, if that's potentially possible.
That'd be amazing if I could. No, I can't do that just yet. It's a fairly straightforward tool. It uses just PHPP. And it is possible to take any EPD though and just look through it and enter it yourself, because it has a library, a central library of EPDs which you can add to. So there's that possibility. But as far as the API is concerned, that's a little bit beyond the capability of the tool, I'm afraid. Yeah. Okay. It would be amazing to get hold of. Well, any EPD that you can get hold of, you could potentially enter yourself.
Fantastic. Great. And then the other question I'd like to end with is the balancing, because I think where these tools get really interesting is some of it's sort of the merging of calculating both the operational and the embodied carbon of buildings, and putting that together in a way that can be assessed in a holistic manner that we've been missing. And I think, Jason, you really looked at that, and Tim also, the final analysis of like what's the real balance is what we've been chasing for a long time. So I don't know if any of you, I'd like to put that out to the general thing, and maybe raise your hand so I can see if you're interested in speaking first, and we can address that balance, real whole building assessment.
Yeah, let me start with that one. So one thing I didn't say in my presentation is having PHP variant file linked to LCA quick, even once I had the linkage working, was fairly painful. So it still takes me about 8 hours to take a new passive house building and get LCA linked up and getting it so I can run through a variance file. But certainly in our practice, I'd like us to do embodied carbon for every single building. We do a PHP file for every building we do. And we do a variance file and we show the building at various stages so the client can select what energy level they want to perform at. I want, at the same time I do that, I want to have the embodied carbon on there to some level, so that it's no additional cost to the client. They can actually see what they're going to get and what they're choosing to do long term. And so to me, getting to that phase needs to happen, and it needs to happen in a way they can use. And Tim, if I'd seen your tool before I started, I probably would have used your tool instead of LCA Quick, because it certainly is faster than that. LCA Quick's is obviously better for us because it's localized. But yeah,
you've got a big database in there. That's really useful. That's very useful.
Yeah, Brands did a great job. Oh yeah, to be clear, I just used the tool. I didn't help develop it.
So maybe Stacey and then Tim, you can close off on that whole energy balance, the operational and embodied assessment.
Stacey. Yeah, it's vitally important. I mean, I think the way that EC3 came to be was that, in my role at Skanska, we started showing our clients, just based on benchmark data, that breakdown in our interviews and our proposals of, you've been looking at this operational stuff, look at this embodied carbon bucket, we've got to figure out how to address this and really reduce it, not just track it. So I do think it's something that once someone understands it, or at least sees the potential of what their project's going to be, there's a desire to focus on it and reduce it right alongside operational. I think the output side, in EC3, there's once you build a project and you've got your kilogram of CO2 per square foot or square meter, you can put in an EUI and an energy profile, and it will do that comparison for you. So that's really our first kind of, at least quick fix, where it gives you that comparison for your project, and you can kind of control those energy inputs. What we hope is that someone's going to take our API with the emissions data and build it into more robust energy modeling tools, where it's actually just pulling in the emissions factors for all these things that you're modeling into your envelope system. And our API is open and free, so anyone who wants to try that can, and we welcome it. So
fantastic.
Yeah, and on the point of comparing it with other things, what the PH ribbon allows you to do is you would typically compare it with something, a typical standard, a typical construction, equivalent construction that gave the same U value. Say another common method for passive house, perhaps it could be concrete or whatever you think is a standard construction for your region. And so what you could do with there is you can do that in another spreadsheet, and you can just bring it over, just copy it over, and it'll, as long as there's a few ticks and crosses that you can easily put in, which just allow you to set up that second comparison graph. So it's fairly straightforward just to have that comparison as a regular thing that you do, and it is important to be comparing, because most people, they look at a graph, they don't know if that's high or is it low, or is it, what are we comparing with there? So it is useful to always have a comparison on, and you could compare with either one thing, or you could compare with a whole complete building with a roof, roof construction, floor construction, wall construction, or you can also just change one thing. If you want to home in on something, you could also say, well, what's this? What if we just chose a wall? How would that compare with this wall? So I think that's all really important to make it clear what's going on.
Wonderful. Well, I thank you all so much for sharing your knowledge. And this is one of the joys of the network, is that we get to connect people on a global scale, all doing similar things, and put you all in the same room, virtual room this time. So thanks again for being here and sharing this information. I'm really excited to see how we can, as a community, push this forward and help really expand the transparency of our carbon footprint for buildings.
Thank you.
Thank you very much.
Thanks much.